Bismillahirrahmanirrahim. Alright class, Assalamu alaikum and welcome to the first lecture of week 8, where today we are going to apply Gauss's law to asymmetric cases, meaning that the cases where the charge distribution is very asymmetric, meaning no symmetry is there. So the effect of this charge density, that is electric flux density, is also asymmetric, and it is so much asymmetric that we are not concerned about the exact charge arrangement, and we cannot in fact determine the exact charge arrangement. So let's see how we can treat this case. Okay, so the electric flux density is very much asymmetric, and definitely no symmetry exists means that we cannot apply spherical coordinate system or cylindrical coordinate system. So in the most generic case where no symmetry exists, so the workhorse which would definitely give us some results is the Cartesian coordinate system. So we are going to use the right-handed Cartesian coordinate system, where there is some electric flux, random arrows flowing from one direction to another direction. So I'm not drawing that particular field because we don't know the shape of the field, but you can understand that the field is pretty arbitrary. So I also want to give you a two-dimensional picture of that three-dimensional scenario which I'm going to sketch here, and we will be interested in x and z axis and y axis is going into the board. All right, right-handed coordinate system. So now imagine that there is some very arbitrary field, electric flux density. So there must have been some source of that field, arbitrary arrangement. We are not interested. We cannot find that source. And we are taking a point P somewhere within this three-dimensional space. And if I want to see it from this perspective, meaning if I am standing on the negative y-axis and watching this scenario, I'll get that P somewhere here. Okay, the coordinates of P are x, y, and z, where we will be as much generic as possible because we don't know about the nature of the field, so we won't use any specific values of x, y, and z. And by saying that flux density is generic, it's very asymmetric, we should take the most generic form of most generic equation or expression of electric flux density. So in the most general case, the electric flux density can have an x component, it can have a y component, and it will have a z component. So this is the most generic. If we would assume that z component is not there, we are not doing any assumption. We are just considering the most generic distribution of electric flux density that might be possible. And not only that, dx, that is the x component, dy and dz, all are functions of x, y, and z. So we can say that dx is a function of x, y, z, dy is a function of x, y, z, and dz is a function of x, y, and z. So we are considering the most generic case that may be possible for the distribution of electric flux density. So you obviously, if we are considering extremely generic case, no assumption whatsoever, so we will have to go through some difficult procedure to get our results. However, the results which we'll get we would be able to apply those results everywhere, in each and every situation, even in symmetric cases, because symmetric cases are nothing but special cases of asymmetric cases. So we have not only we have used the generic coordinate system, which is Cartesian coordinate system, but we are also considering the most generic distribution of electric flux density, which is having x component, y component, and z component. And not only that, we are saying that x component is a function of x, y, z, y component is a function of x, y, z, and same as for the z component. Okay, so if we want to find electric, and one more thing, at this point, let's say we know the flux density, let flux density capital D at point P, which has got the coordinates x, y, and z. Let D at P be D naught. Let's say the flux density at point P is given by D naught, and since we are taking the most generic case, so that D naught can be given by its x component, y component, and z component. So this is what we are going to represent. This is how we are going to represent the value of electric flux density at point P, which is D naught. So because we don't know exactly the expression for this, so we are also writing the most generic expression for electric flux density at point P, which is D naught. Okay, so having said that, let's try to apply Gauss's law, meaning this expression, which is nothing but closed loop integral, closed loop surface integral of d dot ds of the dot product of electric flux density and the surface at every point on that surface gives you the total charge enclosed by that surface, or which is equals to, according to Michael Faraday's experiment, the total flux passing through or going across that closed surface. So let me repeat it again. The closed loop meaning the surface is closed, there is no open hole in that surface. The closed loop surface integral of the dot product of electric flux density and the surface at every point, differential surface meaning we are taking one point at a time on that surface. This integral will give us the total charge enclosed by this closed surface, which will be equal to the flux crossing that surface. So ये इंटीग्रल इवैल्यूएट करने से हमें क्या मिलेगा, वो चार्ज मिलेगा टोटल जो उस क्लोज सरफेस के अंदर बंद है, और उतना ही फ्लक्स उस सरफेस से क्रॉस होके बाहर निकल रहा है, उस सरफेस के आर पार जा रहा है. ठीक है. Alright, so now applying Gauss's law. Let's apply Gauss's law. Now for Gauss's law we must choose a closed surface. Okay, so we are choosing a closed surface around this point. Okay, and definitely we know that we are working in Cartesian coordinate system, so the closed surface which we can choose would be a cube. Okay, and we are choosing the surface so that that point P, over which we know the value of electric flux density to be D naught, that point is exactly at the center of that cube. So if I want to see the two-dimensional version, so we are taking we will see a square instead of a cube in 3 dimensions. Okay, cube in 3 dimensions, square in 2 dimensions. And let's say this volume is incremental volume, and its width is given by delta y, and its depth is definitely given by delta x, and its height is given by delta z. Okay, so the formula for incremental volume would be delta x, delta y, and delta z. So this height is delta z, and this width is delta y, sorry, delta x, okay. So now we want to apply Gauss's law on this surface, where we know that this finite incremental volume is made up of 6 infinite surfaces, one at the top, one at the bottom. Z equals some other quantity, y equals some quantity, y equals some other quantity, x equals some quantity, x equals some other quantity. So let's say that the front, this one, the x equals constant which is facing us, we'll call that surface to be the front surface. The x equals constant which is at the background, we'll call that back surface, and the z equals constant which is at the top, we'll call it top surface, and z equals constant which is at the bottom, we'll call that bottom surface. Similarly, for y equals constant on the right, we'll call it right surface, and for the left, we'll call it the left surface. So if I want to apply Gauss's law, meaning that I have to evaluate this integral d dot ds. I am deliberately omitting this subscript s here because now you know that d is nothing but electric flux density. So if I apply it like this, this time the expression for all the 6 surfaces are different. Earlier we in the symmetric case we did 2 examples, in which one with the first was point charge, the other was infinite line charge. For point charge we had only one spherical surface, so for that spherical surface we had only one formula, and for the infinite line charge we had 3 surfaces, one cylindrical and 2 top and bottom z equals constant planes. So in that case we had to divide this integral into 3, but since the integral for the top and the bottom was 0, so we were considering only for integral for the cylindrical surface. But now this time we don't know what's the direction of field while the field is passing through any of the 6 surfaces. So what we will do, we will break this integral for all the 6 surfaces, one for front. I'm not repeating the integrand here just for the sake of time. One for back, one for top, one for bottom, one for left, and one for right. Okay, this is equation number 1. Okay, we'll have to divide this integral into 6 integrals. Why? Because for each of the 6 surfaces, the formula for ds would be different. Now you would argue that the formula for the front surface and formula for the back surface would be the same, which is delta y multiplied by delta z. That's true, but we know that the differential surface or incremental surface is a vector quantity, so we must have a vector associated with each of the surface. So for the front surface, which is the x equals to constant surface, which is facing u, that surface would have ax as the unit vector associated with that surface, or the direction associated with that surface. While for the back surface, all right, the magnitude would be delta y multiplied by delta z, delta y multiplied by delta z, but for that surface the direction of unit vector will be minus ax, because it is convention, it is tradition. This is how we define everything in electromagnetic fields, that surface always points outside the volume, which is this q. So for front surface, the direction of the surface is ax, for the back surface it is minus ax. So for every surface we'll have to divide it. And notice that I am not using any closed loop here, because now each surface, front or back or top or bottom, each surface is not a closed surface. Yes, they combine together, all the 6, if we combine them all together, what we'll get a closed surface. So on the left hand side we have closed surface for surface, but on the right hand side we have got 6 open loop integrals, and for every integral there should be d dot ds, but for the sake of time I'm not writing it here. Sorry, I should write this top here. Okay, so now applying Gauss's law. So let's start evaluating the integral for the front surface. Okay, now remember that we should remember that this integral will give us the total charge enclosed or the total flux leaving. Total flux leaving is important. So total flux leaving this closed surface. Okay, so what should this give us? This integral should give us the total flux leaving through the front surface. Okay, and similarly for this integral will give us the total flux leaving the back surface. This will give us the total flux leaving the top surface, the bottom surface, the left surface, the right surface. Add them all together and you'll get what? You'll get the total flux leaving a surface. So this is what we should expect. This integral, the first term on equation number 1, on the right hand side of equation number 1, the first term will give us the total flux leaving the front surface, which is almost equals to the flux which is passing through the front surface dotted with the surface area or incremental surface for the front surface. Okay, and this front is, so let's say I'm just changing the orientation a little bit, and let's say this is the front incremental surface. Okay, and let's say from this surface, through this surface, this is the electric flux density which is leaving. We'll call it this d front, and definitely if I resolve this d front into two components, one component will be parallel to the patch or the surface area, and one will be perpendicular to patch, and the perpendicular is the one which is responsible for the flux, and that component is actually leaving or crossing the surface area. The other component is flowing parallel to, is just flowing or moving parallel to the surface, so it is not actually crossing. So I'm not interested in that one. So I'm interested in the in that component of d front which is parallel to the direction of the patch. So direction of the patch is this one, perpendicular to the patch itself. So I am interested, this is theta, I am interested in the dot product which will give me the component of the flux density which is parallel to the direction of the patch, which, and that component of d front is actually crossing or leaving the surface, this volume, leaving this volume through the front surface. Okay, all right, so why this is almost equals to? Because if this differentials, if this incremental area, this patch is not sufficiently small so that only one flux line is crossing through it, then this equality will become almost equal, because we are taking only one flux line and treating it to be as if this flux line is true for whole surface area. Okay, if it is not the case, if I have chosen the differential area, sorry, the incremental area not so small, so there may be another flux line passing through it in this fashion. Now which one should I resolve and which component should I count here? Okay, So that's the reason why we are using almost that. This surface area is very small, is so very small that we are considering that maybe only one flux line is passing through it, because this, geometry or trigonometry which we are trying to do, we are considering that through this patch only one flux line is moving in one direction. But if the patch is not that small, that only one line is passing through it, one different is passing through it, maybe more than one, two or three different are passing through this differential patch, in that case our results will be inaccurate. To make them accurate, later on, as you might have guessed, that later on we will apply a limit that this surface area is so small that this incremental area would become a differential area. In that case, we will reduce this differential area to be treated as a point. So we'll reduce this incremental to differential entity, and in that case we would be able to say for sure that only one flux line is passing through that differential area, which we are not considering right now. So we are just for this this reason, what we are doing, we are using not exactly equal but also almost equals. All right. So if we would take only exactly equals to, I mean, if this patch is so small that I can treat it to be a point, then there is no need to do integration. Flux leaving that point is nothing but the dot product. Since I'm not using that since I'm not defining at this moment, I'm not defining this surface patch to be differential, rather I'm defining it to be incremental. So I'm using almost equals to. Why? Because because this front surface is actually, so far it is incremental, we have taken it to be incremental, so it is almost equals. So I think I should remove it from here. Okay, so now what we can do, we can write it like this: front dotted with, for the front the formula is delta y delta z ax, and the flux which is passing through front surface may have, definitely, because we are considering a general case, may have an x component, it may have a y component, and I hope you would be able to see it, it may have a z component. Okay, it may have x, y and z, because we don't know what kind of flux, or in what way, in what orientation would the flux density would pass through the front surface. So we have no choice whatsoever other than to take all or consider all the three components, other than considering all the three components. Okay, so this is the flux density passing through front, which generally can be defined as this. But once you will evaluate this dot product, obviously this dot product, we have one component, one vector has got all the three components, the other component has got only one component. So after taking the dot product, what will be left? Only the x component of the x component magnitude, this is d front x, would remain, and magnitude of the second vector would remain. Okay, there are two vectors, d front, the other vector is ds front, okay, which has only x component. This one has got three components. So after evaluating the dot product for this d front, only x component would remain. The magnitude of this x component of d front and the magnitude of the second vector would remain, and rest would be if you take dot product, the rest of the components would be 0. So now let me call it equation number 2. So in equation number 2, since we have chosen the closed surface, we know these two things, but what we don't know is that what is d front, what will be the x component of the flux density, scalar x component of the flux density which is passing through the front surface. Okay, we want this, we don't know what that is in equation number 2. Now to find that we need to do some some intelligent work. So let's say, just for the sake of argument, let's say electric flux is flowing in this direction through this point, okay, and we know that at this point the x component, what we need the x component of the electric flux density which is passing through the front surface. Now remember that if you will see this situation from here you are standing, you're watching this situation. So x-axis is on your right hand side, you're standing here, and z-axis is going up and y-axis is going away of you. So this is exactly the situation which I showed you. X-axis is going on your right hand side, you're standing here, and z-axis is going up and y-axis is going away of you. Okay, so the front surface, if you are standing from here, the front surface would lie on your right hand side. So this let me embolden this right hand, this is still the line, I've just emboldened it. So this is the front surface, remember that this is front surface, okay, and this is the top surface, this is the bottom surface. This which is now in this orientation on your left, this is the back surface. Okay, so I'm not changing it, I'm just handling the front surface right now. So the x component of the flux at this point is known to us, and that is d naught x. Okay, what we need the x component of the flux which is leaving through this surface. Okay, what we can do is some intelligent mathematics, that this distance, we know that if this whole width is delta x, so this distance is delta x by 2. Okay, so let's say, don't consider it to be a flux line, consider it to be a particle which is moving, any particle, a speck of dust is moving, मिट्टी का एक जर्रा यहाँ से उड़ता फिर रहा है, and what you have done, when that मिट्टी का जर्रा came here, you captured it. You have a camera, high speed camera, you captured it, and you found out that the velocity at this point is v naught. Okay, let's say v naught, d naught. Okay, it's a very weird way to represent velocity by d, but we are taking it to be, let's say this is the velocity, because remember that velocity also belongs to the flux density type of vector field effect. So definitely this is also the electric flux density also belongs to the same group. So let's say the velocity at this point, the velocity of that speck at this point is given by d naught, and the x component of that velocity is this. What you want to do, you want to find out the velocity of that speck when it would reach the front surface. So you know the velocity, x component of the velocity at this point, you know this distance. If somehow you know the rate at which the velocity is changing during this distance, you will be able to find the velocity, x component of velocity at this point. Okay, so the x component of velocity through the front surface will almost be equals to the x component of the velocity at this point plus rate of change rate of change of velocity in that case, but we'll say rate of change of x component of flux density with respect to x, take it and multiply it by the distance between these 2 points. Rate of change of dx with respect to x, because while moving a speck from here to here, the component of velocity will have the z component, will have the x component, and may also have the y component, but we are not interested in that. What we are interested in is the x component of the velocity when it passes through this point, and we know the x component of velocity when the speck was already here. जब मिट्टी का जरा यहाँ पर था already, उस वक्त x component, velocity का x component क्या था हमें पता है. हमें निकालना है जब वो मिट्टी का जरा इस front surface के पास के थ्रू गुजरे, तो उस वक्त वेलोसिटी का एक्स कंपोनेंट क्या है. अगर मुझे एक्सेलरेशन पता हो, यानी रेट ऑफ चेंज ऑफ वेलोसिटी ड्यूरिंग दिस डिस्टेंस, जिसके दौरान मुझे मालूम करना है, अगर मुझे रेट ऑफ चेंज ऑफ वेलोसिटी पता चल जाए, रेट ऑफ चेंज ऑफ वेलोसिटी एक्स वाई जेड हर एक का नहीं चाहिए, मुझे सिर्फ एक्स कंपोनेंट में कितना चेंज आया, क्योंकि मुझे वहां पे एक्स कंपोनेंट में इंटरेस्ट है. So rate of change of x component of velocity with respect to x, because I want to see that if I move from this to this and this direction, if I move from this point to this point, how much would be the change in the x component of electric flux density. So I want to see the change in magnetic x component of magnetic flux density while I'm moving in x direction only and only. Okay, so this, whatever is written in this bracket, can be given as rate of change of dx with respect to x. Why partial differentiation? Because dx, as I said before, which I rubbed at, dx will be a function of x, may be a function of x, y and z generally, so we are taking it partial differential. So this is the bracketed term, multiply by delta x by 2. So this was the x component of electric flux at this point, and the second term is the change which happened, in the x component of electric flux during this duration while traveling from this point to that point. So the second term is just a change that happened in the x component of electric flux during that duration, and we just added this change into the in the original, in the x component of the flux at this point. Original value of x component of flux at this point. It's that simple. All right, so if I would just rearrange it, so I would like to write it like this term first and this term at the second place. Nothing much important. So equation number 2, from equation number 2, now I'll get the front d dot ds, which is almost equals to, this is what, this dx naught plus delta x by 2 dou dx over dou x. This is what? This is d front x delta y into delta z. This is what we would get. Now stop here. Now I want, I've got this. Okay, there is no unknown so far except maybe this thing. Okay, so let's try to find integral for the back, or the amount of flux which will be leaving that volume through the back surface. Okay, let's try to do that with this red pen. That would be equals to, we don't need to repeat everything again. I want to find the integral for the back. Okay, I hope you would be able to see it in red. So for that, what we need d back dotted with delta s back. हर चीज जो front वाली थी, that will be replaced by the back one. Everything which was belonging to the front will be replaced by back. So d front instead of d front, d back. Now for this d back, we have already discussed that this time we'll have to use a negative sign here for the direction. Okay, so the negative sign for the direction, and instead of front we have to use the back. Integral electric flux density back and y, sorry, not y, still, because through the back only x component would be there. Okay, so equation, that would be equation number 3. Now to find d back, the x component of d back, what we would need, dx naught, instead of adding this time this change, the second time remember it was change, instead of adding the change, now subtract the change. Whatever you did previously for the front, do the exact opposite of that. So do exact opposite of that. The rate of change is the same, but what we are doing, previously we added that change, now we are subtracting that change. So now integral for the back, finally I can write it here, would be equals to minus sign. So from equation number 3 now, minus sign comes, then d back x is nothing but dx naught, this time minus delta x by 2 dava dx by dava x, and this remains the same, delta y and delta z. Great. Now once we have got the expression for front and the back, before moving on for the top, bottom and left and right, let's try to add these two. So integral front plus integral back, I'm not writing the integrands right now, will almost be equals to, adding these two together will cancel the dx naught, and the rest of the things will be added because of the minus sign outside the bracket. So dava dx over dava x multiplied by delta x, delta y and delta z, and we know that this product is nothing but the differential incremental volume which we chose. So why not write it like this, and I'm going to call it equation number 4. So you see that for the front and back component, what we got is volume, incremental volume, times the partial derivative of x component of d with respect to the the coordinate variable x. So from here, if we would repeat every step for front, for top and bottom, for right and left, what will end up in, I'm just writing it from through observation. Curious students can definitely try to evaluate each integral separately, but observing equation number 4, I can see that integral for top plus integral for bottom will give me, because for top and for bottom the constant planes are z, will get the addition dou dz over dou z multiplied by volume. For front and back, the constant planes were x equals constant. For top and bottom, the constant planes are z planes. So I'm just making use of my mind, which Allah subhanahu wa ta'ala gave me, left and right. For left and right, and you can try to do it at your home yourself. So for right and left, the constant planes are x equals to y equals to constant plane. So we would be interested in this. What we'll get is this. So now, if that's the case, right color always sticks. Okay. So from equation number 1, if we add this equation number 4, equation number 5, and equation number 6, what we'll get? We'll get equation number 1, which is on the left hand side is d dot ds closed loop integral, and if I just add all the right hand sides, taking delta v to be common, what I'll get? I'll get dou dx over dou x plus dou dy over dou y dou dz over dou z whole multiplied by this. Wow. And what is this equals to? This thing equals to charge or flux. So now, and this is approximately equals to make it exactly equals to, we'll have to apply the limit. So if I just cross multiply this, and I'm writing the second term, okay, first dou dl, all this plus dou dz over dou z, okay, and this on integral d dot ds, and cross multiplying by delta v means that this will almost be equal to this, which is equals to q upon, what we are doing, we are rearranging this expression and dividing the whole expression by delta v, which is equals to psi divided by delta v. So to make this almost equals to, exactly equals to, what we'll have to do, we'll have to apply a limit that delta v tends to 0 everywhere. Delta v tends to 0, limit delta v tends to 0. Okay, so let me call this expression, and by the way, what's this? Charge per unit volume, where volume is shrinking to be 0. What's this? This is rho v. So let me call this big, very big equation to be equation, because this is big, let's call it alpha equation, and we'll talk about this alpha equation in the next class. Till then, assalamu alaikum.